Hello everyone, and welcome to this mathematical presentation. Today, we are going to explore a fascinating question in complex analysis. What is minus 1 to the I? This may seem like a strange expression. How can we raise the negative numbers to an imaginary power? And what kind of results we get? As we'll discover, the answer is both surprising and beautiful. The exploration will take us through ordered formula, multi-valued function, and the beautiful connections between algebra and geometry. Let's to solve it. The question is, what is the minus 1 to the power of I? This is a complex number. There are some observation. Minus 1 to the I is a complex exponential. It involves an imaginary exponent. The base of minus 1 is a real number. We need Euler formula to evaluate it. This is just a special case of a to the b with complex exponent. We know that the a to the b, but when the exponent is complex, the s to the is different. The Euler formula, we have e to the I theta equals to cosine of theta plus I sine of theta. This is there are some important identities from this formula. E to the ip equals to minus 1 and e to the ip over 2 equals to I. E to the 2ip equals to 1. So key identity for all problem is minus 1 equals to e to the iv equals to e to the I multiply p plus 2kp for any integer k. We use this formula to prove the equation. Complex multi-valued. Why minus 1 to the I multi-valued? Because minus 1 can be written as minus 1 equals to e to the ai multiply p plus 2kp. K is integer numbers. Therefore, minus 1 to the I equals to e to the I multiplying p plus 2kp equals to e minus 1 because I multiply I equals to minus ln. So we can write minus 1 to the I equals to e to the minus p plus 2kp. And so minus 1 to the I equals to e to the minus p multiplied e to the minus 2kp. This gives the infinitely many values for different number of k's. The principal value uses the k equals to 0. So if we assume k to the equals to 0, so minus 1 to the I equal to e to the minus p, and e to the minus p approximately equal to e to the minus 3.14159265535, approximately equal to 0.043239. So minus 1 to the I equals to a real value. The principal value minus 1 to the I equals to 0.043239. This is a real number. Positive at less than 1. This is the surprising. What value of minus 1 to the I? The complex set of value for k integer numbers. Minus 1 to the I equals to e to the minus p plus 2kp equals to e minus 3 multiplied e to the minus 2kp. For some value of k, we can see the different value of minus 1 to the I. For k equals to 0, e to the minus p approximately equal to 0.043239. For k equals to 1, we have e to the minus cp approximately equal to 0.0000807. For k equals to minus 1, e to the minus phi, e to the p equals to 23.1407. For k equals to 2, the value is e to the minus 5 pi approximately equal to 60.51. And for k equals to minus 2, the value equals to e to the 2 pi approximately equal to 123,910.6 is the large value. So we can calculate for other values too. Also, we can use the logarithm approach using the complex logarithms, like how a to the b equals to e to the b multiply ln a. For complex number, ln minus 1 equal to I multiply p plus 2 kp. K as is integer numbers. Therefore, minus 1 to the I equals to e to the I multiply ln minus 1 equals to e to the I multiply p plus 2 kp. So equals to e to the minus p plus 2 kp. This complex logarithm give our branch this, similar to the previous efforts. Also, we have some comparison with other powers. Minus 1 to the n for integer n, minus 1 to the n equal for if n is even, then the value is 1. And if n is odd, then the value is minus 1. For n equals to 1 over 2, minus 1 to the 1 over 2 equals to square root of minus 1 equal to I. So minus 1 to the 1 over 2 equals to I, the principal value, the imaginary values. Minus 1 to the I equals to e to the minus pi approximately equal to 0.04G2139. This is the principal value of the minus 1 to the I. We can see that the minus 1 to the I is real value. Property of we have here, we can see the different property of the property of minus 1 to the odd. For the real value, minus 1 to the I belong to the real value, real set. It is positive, minus 1 to the I larger than 0. Although it is less than 1, minus 1 to the I approximately equal to 0.043239, less than 1. Also, it is multi-valued. Minus 1 to the I equals to e to the minus pi plus 2 kp, and t is integer number. Although in here we can see the connection to the Euler's identity. Euler's identity revisited. We know that the e to the ip equals to minus 1. Raise both sides to the power I. E to the ip to the I equal to minus 1 to the I. So we can see that the minus 1 to the I equals to e to the I2 pi equals to I2 equals to minus 1. So minus 1 to the I equals to e to the minus p. This is a beautiful consequence of Euler identity. Also, there are some generalization of minus 1 to the odd. For the dual pattern for the minus 1 to the I is minus 1 to the z for any complex number z. Minus 1 to the z equals to e to the z multiply ln minus 1 equal to ez multiply I2 pi plus 2 k pi. So minus 1 to the z equal to e to the iz multiply p plus 2 kp. For z equal to I, we had minus 1 to the I equals to e to the I multiplied pi plus 2k pi equal to e to the minus pi plus 2kp. And although for z equals to 1 divided to 2, we have 1 minus 1 divided by 2 equals to e to the I multiplied pi plus 2kp over 2 equals to e to the I pi other 2 plus kp equal to plus minus r. The equation of minus 1 to the I equals to e to the minus pi approximately equal to 0.043139. There are some key points about the minus 1 to the I. It is used the I-net formula e to the I pi equals to minus 1. It is multi-valued e minus 1 to the I equals to e to the minus pi plus 2k pi. And also it has its principal values. E to the minus pi approximately equal to 0.03432139. All values are positive real numbers, and also that's connection to the real identity. The t inside is the minus 1 to the I equals to e to the minus pi. Thanks for watching. See you in next video.